Situation here, we have problem number what?
30.
Problem number 30 on page whatever it is. I gave you the page numbers.
144.
144? Thank you. Page 144. All right, so here we have the moon orbiting the Earth, and here is our orbital radius. Here's the moon. This is not to scale. The moon is actually 60 Earth radii away, or 30 Earth diameters away, but we'll just call this R right here. And we know that R is equal to 3.85 times 10 to the 8th. Is that what we said it was? Meters. Is that correct? 3.85? All right, we know the mass of Earth, and over here we got the mass of the moon. But what can you tell me about the mass of the moon?
It's irrelevant.
It is irrelevant, okay? It talks back to its teachers and parents. It's just completely irrelevant. Oh, that's irreverent. Yes. Okay. All right. So, same situation as before. We're trying to find the orbital period, and we're going to end up getting it when we use SI units and all the units that we have. We'll look at it dimensionally, but our answer is going to be in what units? Seconds, right. If we use all SI units and derived units, then they're all going to collapse back down to seconds if we're solving for a time. This question asks us for it in terms of days, and then we're going to compare that to what? To a month, okay? And the word month and moon come from the same place, right? Many moons ago means many months ago. All right, so here's the idea. We're going to go ahead and set it all up all the way back to the beginning. We're going to say net force is equal to mv squared over r, but we're not looking for velocity. What are we looking for? Period. All right, so that's equal to 4 pi squared r. I'll use capital R since we're using that up there, over t squared. All right, and we know the net force. This is how much force we need. Where does the force come from, guys and girls? From gravitation, right? So GMM over R squared. All right, so we're going to take those and set them equal to each other, as we are wont to do. And we get that m times 4 pi squared r over t squared is equal to GMM over R squared. Big M, little m. All right? So what is little m? What is big M? Little m is the mass of the moon. As we said, that our result is independent of the mass of the moon. Snow day at the Vatican. Cancel mass. All right, so we know that it's just strictly a function. Velocity is a function of the distance, the orbital radius. It has nothing to do with the mass of the object. If we wanted to put a Volkswagen in orbit at the moon's distance, it would have to have exactly the same speed. It doesn't matter if it's a Volkswagen out there, a concrete truck. It doesn't matter if it's a nickel. It doesn't matter. If we're going to have a stable orbit at that distance, it has to have the same velocity and therefore the same period. All right, so now we're just going to rearrange this algebraically to solve for period. We get t is equal to the square root of 4 pi squared r cubed over gm. Okay? Now, to be a little bit more nice about it, we'll put 2 pi out here, and we'll say r cubed over gm. So now we said that our unit should turn out to be what? Seconds, right. Period is measured in seconds. So r is a distance, right? So r is radius. That's going to be meters cubed. And then we're going to divide by g, which is Newton meter squared per kilogram squared, right? So a Newton is a kilogram meter per second squared. So that's the Newton. Kilogram squared per meter squared per kilogram squared, sorry. Meters squared per kilogram squared. And so now we have that's G, and then M is going to be mass, so what's that going to be? Kilograms again. All right, so dimensionally, this kilogram squared is canceled by these kilograms. We got meters cubed on the top. We got a red pen on the floor. Meters cubed. So we got 1 over second squared to the 1/2. That's going to be equal to seconds. Hey, it works out. All right, so the radius that we're looking for, period, is equal to 2 pi times the square root of the radius, the orbital radius, we said is 3.85 times 10 to the 8th meters, and we're going to cube that. We're going to divide by 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. We already worked all that out dimensionally. We know that we can just collapse it all down to seconds. and then we still have to multiply by the mass of Earth, which is equal to 5.98 times 10 to the 24 kilograms. All right, this looks like a pretty big function here. So be careful as you put it in your calculator. Please, in these situations, use the exponential, not the exponential, the scientific notation function in your calculator so you don't run into order of operations struggles, right? If you do this if you use the scientific notation button, then all of these end up being numbers, not expressions when you're multiplying by 10 to the whatever. Because you end up having some things under the radical and other things not by order of operations problems, okay? So I'm just going to pause this for a second while we do those calculations. All right, so that's our period in seconds. We want period in days. So we have to do a little factorial label method. 2.42 times 10 to the 6 seconds times 86,400 seconds in a day. If you don't know that, you can do seconds per minute, minutes per hour, hours per day. But we know from the song that it's 86,400.
There's a song.
That's a different song, you know, right? Okay, thank you. T is equal to, how many days does this turn out to be? To our precision. We have 3 sig figs here, so let's stick with 3 sig figs. 28.0? Okay, 28.0 days. Now, the real number, or the accepted scientific number, is approximately 27.3 days. All right, now I want to take a second to, so this is pretty close. We're happy with this. But I want to take a second to explain to you, is that longer or shorter than a month? That's shorter than a month. All right, now. All right, I want to take a few minutes to explain something to you, but I'm going to do it on a different video.